What if the greatest discovery in human history lies not among the stars, but miles beneath the ground we walk upon every day? What if the hollow spaces within our planet shelter intelligences far older and more advanced than our own? What if everything we believe about Earth's interior is merely the surface of a much deeper truth? Tonight on Slumber Expeditions, we explore one of humanity's most persistent and captivating mysteries, the possibility that beneath the familiar crust of our world exists another realm entirely, perhaps even inhabited by civilizations that have evolved in darkness, pressure, and isolation for millions of years. We will journey through centuries of exploration, scientific discovery, and speculative wonder, examining the evidence, theories, and tantalizing hints that something profound may exist in the deepest places of our planet. From ancient legends of underworld kingdoms to modern discoveries of vast subterranean oceans and ecosystems thriving in conditions once thought impossible for life, we will trace the evolution of this compelling idea and ask whether the final frontier might not be space, but the uncharted depths below. So before you settle in, if you're finding comfort in these subterranean mysteries, please consider liking this video and subscribing to the channel. But only if you genuinely like what we do here. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with a global community of curious minds who share this fascination with the hidden worlds that may exist just beyond our reach. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's speculative journey together. Let the weight of the world above fade away as we descend into the unknown. You're standing at the entrance to Mammoth Cave in Kentucky on a cool autumn morning in 1838, lantern in hand, about to follow explorer Stephen Bishop into passages no surface dweller has ever seen. The limestone opening before you exhales cold air that smells of minerals and ancient water. Bishop, an enslaved man who would become one of the greatest cave explorers in American history, leads you forward with confident steps, his lamp casting dancing shadows on walls carved by rivers that flowed here millions of years before humans walked upright. As you descend deeper, leaving behind every trace of sunlight, you notice the temperature remains constant, the air still and patient. Bishop pauses at a vast underground river, its black waters flowing silently toward chambers he has not yet mapped, and tells you that he believes these passages extend far deeper than anyone imagines, perhaps connecting to great hollow spaces within the earth itself. Standing there in the profound darkness, feeling the immensity of rock pressing down from above and the unknown vastness stretching out in all directions, you realize that humanity has barely scratched the surface of what lies beneath. The concept of a hollow or inhabited Earth is far older than modern cave exploration. Ancient cultures across every continent developed elaborate mythologies describing realms beneath the surface world. The Greeks spoke of Hades, a complete underworld civilization of the dead ruled by a god of the same name, accessible through certain caves and chasms. The Norse described Svartalfheim, the realm of the dark elves, existing in caverns deep within the world. Hindu cosmology detailed Padola, a magnificent subterranean region divided into 7 layers, each more wondrous than the last, inhabited by the Nagas, serpent beings of great wisdom and power. Buddhist traditions described elaborate hell realms and paradises existing in layered dimensions beneath the earth. These were not mere symbolic constructions, but were understood by their cultures as literal places, as real as the mountains and seas, simply existing in a dimension of depth rather than breadth. What makes these myths particularly intriguing is their remarkable consistency across cultures that had no contact with one another. From the indigenous peoples of North America, who spoke of emergence from subterranean worlds, to the Aboriginal Australians, who described the dreamtime emerging from beneath the ground, to the Tibetan traditions of Agartha and Shambhala existing in vast cavern systems beneath the Himalayas, the theme repeats with striking regularity. These traditions often describe the underworld inhabitants as possessing advanced knowledge, spiritual wisdom, or technological capabilities beyond those of surface dwellers. The persistence of this motif across human cultures suggests something deeper than mere storytelling. Perhaps it reflects an intuitive understanding that the Earth contains far more complexity than what we observe on its surface. Or perhaps it preserves fragmentary memories of encounters with phenomena we do not yet understand. The scientific investigation of Earth's interior began in earnest during the 17th century, though it remained largely theoretical for centuries afterward. In 1692, Edmund Halley, the astronomer famous for the comet bearing his name, proposed that Earth consisted of nested spheres separated by atmospheres, with each shell potentially habitable. Halley was attempting to explain anomalies in the Earth's magnetic field, which seemed to require multiple sources of magnetism at different depths. His hollow Earth model suggested that these spheres might rotate at different speeds, creating the observed variations in magnetic readings. While his specific model proved incorrect, Halley was engaging with a genuine scientific puzzle using the best theoretical tools available to him. The idea that Earth's interior might contain spaces large enough for habitation entered scientific discourse, not as fantasy, but as a serious attempt to explain observed phenomena. Throughout the 18th and early 19th centuries, the hollow Earth theory found numerous advocates among scientists and explorers. Leonhard Euler, one of history's greatest mathematicians, proposed that Earth contained a single hollow space with the sun at its center providing light and heat to an interior world. Scottish mathematician Sir John Leslie suggested two inner suns, which he named Pluto and Proserpine, illuminating internal continents. These were not fringe figures, but respected scientists working within the limitations of contemporary knowledge about geology and planetary formation. Without the ability to directly sample the deep Earth, and with only rudimentary understanding of seismology, density, and heat transfer, the interior of the planet remained genuinely mysterious. The hollow Earth theory represented a valid hypothesis, given the available evidence, or rather, the absence of contrary evidence. The most influential early advocate of an inhabited hollow Earth was John Clovey Sims Jr., a decorated American military officer and veteran of the War of 1812. In 1818, Sims proposed that Earth was hollow and habitable within, containing several concentric spheres with openings at both poles approximately 4,000 miles in diameter. He spent years lobbying the United States Congress to fund an expedition to the North Pole to locate the opening and explore the world within. Sims lectured extensively across America, attracting significant public interest and support from some scientists and public figures. His theory influenced numerous works of fiction, including Edgar Allan Poe's The Narrative of Arthur Gordon Pym of Nantucket, and arguably inspired Jules Verne's Journey to the Center of the Earth. Sims died in 1829, still advocating for his theory, still seeking funding for an expedition that never materialized. What makes Sims particularly interesting is that his theory was not based purely on speculation. He pointed to the migration patterns of certain animals, particularly birds and marine mammals, that seemed to disappear into the far north and south, suggesting they might be traveling to more temperate interior regions through polar openings. He noted reports from Arctic explorers of warmer currents and open water in regions that should have been frozen solid. He cited observations of unusual compass behavior near the poles. While these phenomena have since been explained through conventional geology and meteorology, They represented genuine mysteries in Sims's time. His theory attempted to account for observed facts using a bold but internally consistent model. The scientific method requires proposing hypotheses and testing them against evidence, and Sims was doing exactly that within the context of early 19th century science. The hollow Earth theory persisted well into the 20th century, finding new advocates even as seismology began revealing the true structure of Earth's interior. In 1906, William Reed published The Phantom of the Poles, arguing that explorers had actually reached the interior Earth without realizing it, mistaking the curved inner surface for the outer surface as they passed through the polar openings. Marshall Gardner expanded on this in his 1913 book, A Journey to the Earth's Interior, proposing a 600-mile-wide sun at the planet's core and offering detailed explanations for various geological and meteorological phenomena based on his model. These authors collected reports from Arctic and Antarctic explorers describing anomalous observations, unusual animal behavior, unexpected vegetation, strange auroral effects, compass malfunctions, and wove them into comprehensive alternative models of Earth's structure. By the mid-20th century, seismological evidence had definitively established that Earth possesses a solid inner core, a liquid outer core, a viscous mantle, and a thin crust, not the hollow structure envisioned by Sims and his successors. Earthquake waves traveling through the planet revealed its density and composition at various depths, making it clear that no vast hollow spaces existed in the manner proposed by hollow Earth theorists. The theory should have died completely at this point, relegated to the category of historical curiosities like phlogiston or the luminiferous ether. Yet it did not die. Instead, it evolved, adapting to incorporate scientific knowledge while preserving its essential appeal. The question shifted from whether Earth is hollow to whether it contains cavities large enough to harbor hidden worlds, and whether life of any kind might exist at depths far beyond human exploration. The deepest hole ever drilled by humanity extends 7.5 miles into the Earth's crust. The Kola Superdeep Borehole, located in the remote Pachensky district of northwest Russia near the Norwegian border, was drilled by Soviet scientists between 1970 and 1992. For over 20 years, crews worked around the clock, drilling in shifts, replacing equipment destroyed by extreme heat and pressure, pushing deeper into rock formations that had never felt the touch of atmosphere or water since the Archean Eon, more than 2.5 billion years ago. The project represented humanity's most ambitious attempt to directly sample the deep Earth, to move beyond theoretical models and seismological readings and actually touch the ancient layers of our planet. What they discovered challenged numerous assumptions about the nature of the subsurface world and raised as many questions as it answered. As the drill descended past 3 miles, temperatures began exceeding predictions. At 7.5 miles, the rock temperature reached approximately 180 degrees Celsius, far hotter than models suggested for that depth. This unexpected heat was one of the primary reasons drilling eventually stopped. The extreme temperatures caused equipment to fail and made the rock more plastic, causing the borehole to close behind the drill. But temperature was not the only surprise. The rock at great depth proved far more fractured and porous than anticipated, containing water in quantities that should not have existed at such pressures and temperatures. This water was not recent groundwater that had percolated down from the surface, but ancient, mineralized fluid that had been trapped in the rock structure since its formation billions of years ago. The discovery suggested that Earth's crust contains far more complexity, far more hidden structure than surface observations could reveal. Perhaps most startling were reports of unusual sounds detected during the drilling. In 1989, Several Soviet researchers claimed that sophisticated sensors lowered into the borehole detected sounds resembling human screams and wails, which they interpreted as evidence of something unexpected at depth. While these reports were likely exaggerated or fabricated for sensational effect, and the Soviet Academy of Sciences dismissed them, they captured public imagination and revitalized interest in what might exist in the deep earth. More credible were the acoustic anomalies detected throughout the drilling process, sounds that did not match expected geological processes, vibrations that seemed to emanate from deeper sources, echoes suggesting cavities beyond the reach of the drill. These acoustic signatures, while undoubtedly having conventional explanations related to rock structure and seismic activity, reminded scientists that their understanding of the deep subsurface remained incomplete. The Kola borehole, despite its impressive depth, penetrated less than 1/3 of the way through the continental crust, barely scratching the surface in terms of the Earth's total radius of nearly 4,000 miles. Everything below that depth remains accessible only through indirect methods: seismic waves, magnetic field measurements, gravitational anomalies, and theoretical modeling. The entire mantle, the outer and inner cores, the boundary regions where pressure and temperature create exotic states of matter, all of this remains forever beyond direct human observation. We have sent spacecraft to every planet in the solar system, landed rovers on Mars, and photographed galaxies billions of light years away, yet we cannot reach the bottom of our own planet's crust. This profound inaccessibility preserves a genuine mystery at the heart of our world. Other deep drilling projects have yielded similarly surprising results. The German Continental Deep Drilling Program, which reached approximately 6 miles depth in Bavaria, discovered unexpected fracture zones filled with mineralized fluids. The mineral composition suggested chemical processes occurring at depth that were previously unknown or poorly understood. Microorganisms were found living in these deep fractures, thriving in complete darkness at temperatures above 140 degrees Fahrenheit, deriving energy not from photosynthesis, but from chemical reactions involving minerals and dissolved gases. These extremophiles, as they are called, represented life forms adapted to conditions that seem utterly hostile to biology, suggesting that the definition of habitable environments might need radical expansion. The discovery of deep subsurface life fundamentally changed our understanding of Earth's biosphere. For most of history, scientists assumed that life existed only in a thin layer at the surface, dependent directly or indirectly on sunlight. Plants captured solar energy through photosynthesis. Herbivores ate plants, carnivores ate herbivores, and decomposers recycled nutrients, a cycle entirely driven by the sun's radiation. The deep ocean had already challenged this model with the discovery of hydrothermal vent ecosystems in 1977, where entire communities of organisms lived in complete darkness, deriving energy from chemicals released by volcanic activity at the seafloor. But these vent communities existed at the surface of the Earth's crust, at the boundary between rock and water. The organisms found in deep boreholes existed within solid rock, kilometers below any possible access to surface-derived nutrients or oxygen. Subsequent research has revealed that microbial life exists at extraordinary depths throughout Earth's crust. Studies using samples from mines, boreholes, and underground laboratories have detected living organisms more than 3 miles below the surface. These communities include bacteria and archaea species unknown to science, many of which cannot survive in surface conditions and die quickly when exposed to atmospheric oxygen. They metabolize hydrogen produced by chemical reactions between water and iron-bearing minerals, or derive energy from radioactive decay of elements like uranium and thorium embedded in surrounding rock. Their growth rates are incredibly slow. Some deep subsurface microbes divide only once per century, or even once per millennium, yet they persist across geological timescales, maintaining stable populations in total isolation from the surface world. The total biomass of this deep subsurface biosphere may rival or exceed all life living on Earth's surface. Recent estimates suggest that between 15 and 23 billion tons of carbon are locked up in subsurface microorganisms, comparable to the carbon content of all plants on land. This represents an entire shadow biosphere that remained unknown to science until very recently, despite occupying a volume far greater than all surface habitats combined. These organisms live in a world where time moves differently, where generations span centuries, where evolution proceeds at a glacial pace, and where isolation has preserved lineages that may date back to Earth's earliest days. They inhabit a realm of crushing pressure, searing heat, and absolute darkness, thriving in conditions that would destroy most surface life within seconds. The existence of this deep biosphere raises profound questions about the nature and distribution of life. If microorganisms can survive and reproduce miles beneath the Earth's surface, adapted to extreme heat, pressure, and chemical environments radically different from anything at the surface, what other forms of life might exist in regions we have never explored? The deepest mines reach approximately 2.5 miles depth. The deepest boreholes extend 7.5 miles. But Earth's crust extends up to 45 miles deep beneath continental mountain ranges and at least 5 miles beneath oceanic basins. The mantle extends nearly 1,800 miles deeper still. Could life exist at even greater depths, in forms and metabolisms we cannot yet imagine? Could there be an entire ecology distributed throughout the fractured zones, cavities, and mineral structures of the deep crust and upper mantle, completely isolated from surface conditions, evolving independently for billions of years? While the deep biosphere of microscopic organisms represents one form of hidden subterranean life, the question of whether larger organisms or even civilizations could exist beneath Earth's surface requires the presence of substantial cavities, spaces large enough to permit movement, complexity, and development of advanced biological or cultural systems. For most of history, the largest known caves were impressive but clearly limited in scale. Mammoth Cave in Kentucky, with over 400 miles of mapped passages, represented the extreme of what seemed geologically possible. Then modern exploration began revealing caverns of such immense scale that they challenged assumptions about what the Earth's crust could contain. Hang Son Dom, located in the Phong Nha Bang National Park in central Vietnam, was discovered by a local farmer in 1991 but remained largely unexplored until a British expedition in 2009 conducted the first thorough survey. What they found defied their expectations and required new categories of description. The cave contains chambers so vast that a 40-story skyscraper could fit inside them with room to spare. The largest chamber measures approximately 650 feet high, for 190 feet wide, and stretches for more than 3 miles. Within these chambers, underground rivers flow, complete ecosystems flourish, and weather systems generate clouds and fog. Sunlight entering through collapsed sections of the cave ceiling has allowed jungle vegetation to grow inside, creating surreal underground forests where trees reach toward shafts of light penetrating from the surface whirl hundreds of feet above. The scale of Son Dong forces a reconsideration of what might exist in unexplored regions of the crust. If a single cave system can contain chambers large enough to house cities, what might exist in regions that are geologically stable, far from human detection, and protected from discovery by multiple barriers of rock and water? Vietnam's karst landscape, formed by the dissolution of limestone over millions of years, is just one geological setting that produces large caves. Similar formations exist worldwide, many in regions that remain largely unexplored due to remoteness, political instability, or simple lack of interest. The Veryovkina Cave in Abkhazia, Georgia, extends more than a mile and a quarter vertically beneath the surface, making it the deepest known cave on Earth. Much of its depth remains unexplored, with passages leading to sumps, sections completely filled with water, that may connect to deeper cavities beyond the reach of current exploration technology. China's karst regions contain some of the world's most spectacular cave systems, many discovered only in the past few decades. The Miao Room in the Jebi cave system in Guizhou province ranks among the largest known cave chambers anywhere, measuring approximately 360 feet high, 980 feet wide, and 2,300 feet long, a space large enough to comfortably hold several city blocks of skyscrapers. These caves formed over tens of millions of years as slightly acidic groundwater dissolved massive limestone formations, creating voids that slowly expanded as more water flowed through them. The process continues today, meaning these caves are still growing, still evolving, carving new passages and expanding existing chambers. How many similar structures exist in regions we have never explored? How many lie beneath deserts, beneath the ocean floor, beneath polar ice sheets, in places where surface conditions make their detection nearly impossible? The ocean floor presents particularly intriguing possibilities. Approximately 71% of Earth's surface lies beneath water, and the vast majority of the seafloor has never been directly observed or mapped at high resolution. The few detailed surveys that exist have revealed evidence of substantial cavities within the oceanic crust. Submarine caves, called blue holes, descend hundreds of feet beneath the seafloor, their depths largely unexplored due to extreme technical challenges. Some of these blue holes contain chemosynthetic ecosystems similar to those at hydrothermal vents, suggesting that cavities within the oceanic crust might harbor extensive biological communities. The Marianas Trench, the deepest point in Earth's oceans at nearly 7 miles below sea level, has been visited by humans exactly 3 times, and even these visits involved descending in pressurized capsules that touch the bottom only briefly before ascending. The surrounding seafloor, the cliff faces of the trench walls, the potential caves and fissures extending into the crust below the trench, all remain utterly unexplored. Recent research has revealed that Earth's mantle may contain more water than all surface oceans combined, locked within the crystal structure of minerals like ringwoodite and wadsleyite that exist only at extreme pressure. In 2014, scientists analyzing seismic data and mineral samples found evidence of a vast reservoir of water, not liquid water but hydrogen and oxygen atoms bound within mineral lattices, in the transition zone between the upper and lower mantle, approximately 400 miles beneath the surface. This water exists under conditions of temperature and pressure so extreme that conventional concepts of solid, liquid, and gas cease to apply. But its presence suggests that the deep Earth contains far more complexity than simple layers of molten rock and metallic core. The boundary regions between different pressure and temperature zones might feature conditions where water is released from minerals, creating pockets of fluid, perhaps even cavities stabilized by some configuration of pressure and chemical composition we do not yet understand. Acoustic surveys of the deep ocean have detected anomalous echoes suggesting the presence of large cavities within the oceanic crust and possibly in the upper mantle beneath certain regions. These surveys use sound waves to map the structure of rock layers beneath the seafloor, similar to how sonar maps the ocean's depth. Occasionally, these surveys produce echoes that do not match expected patterns, reflections that suggest voids, chambers, or regions of unusual density. Most such anomalies probably result from complex rock formations, fracture zones, or pockets of fluid or gas trapped within the crust. But some remain unexplained, their acoustic signatures not matching any known geological structure. Without direct sampling, which is technically impossible at these depths, these anomalies remain mysteries, hints that the solid Earth may contain more empty spaces, more hidden structure than our models account for. The discovery of vast aquifers deep beneath Earth's surface adds another layer of possibility. In 2019, researchers announced the discovery of approximately 3 times more water than all surface oceans combined trapped in rock pores and fractures throughout the continental crust at depths up to 6 miles. This water moves slowly through fractured rock, forming underground river systems that dwarf any surface waterways. Some of these aquifers are isolated from surface water cycles, containing water that has been underground for millions of years. The chemistry of this ancient water differs substantially from surface water, enriched with dissolved minerals and gases, supporting unique microbial communities. But the sheer volume of these aquifers suggests that substantial cavities must exist within the crust to contain and channel such enormous quantities of water. Where water flows, erosion occurs, gradually enlarging fractures and creating passages that might, over geological timescales, expand into substantial cavern systems far below any depth humans have explored. As we conclude this part of our journey into the hidden realms beneath our feet, we would like to extend a special thank you for listening. If you are finding comfort in these explorations of Earth's mysterious depths, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you are listening from and what time it is there. It is always fascinating to connect with our global community of curious minds. You can also share which part of the story has captivated you the most so far. It would be wonderful to start a conversation around it. Now, let the mystery of what we have uncovered so far settle in your mind as we prepare to continue our exploration deeper still into theories of what intelligence might arise in such alien environments, hidden from sunlight and surface life, evolving along paths we are only beginning to imagine. The deep subsurface environments we have explored represent conditions radically different from the surface world, where conventional evolution shaped the diversity of life we recognize. Sunlight, oxygen, moderate temperatures, liquid water, and relatively low pressure define the parameters within which nearly all familiar organisms evolved. But the deep biosphere operates under entirely different constraints: complete darkness, extreme pressure, temperatures approaching the boiling point of water, oxygen scarcity or complete absence, and energy sources based on chemical reactions rather than photosynthesis. These conditions seem hostile to life from a surface perspective, yet they have fostered their own forms of adaptation, their own evolutionary pathways. The question becomes whether evolution in such environments could produce not merely microscopic organisms, but complex, perhaps even intelligent life forms adapted to conditions we can barely imagine. Evolution requires 3 fundamental elements: replication, variation, and selection. Organisms must reproduce, creating copies of themselves that are similar but not identical. These variations must influence survival and reproduction rates, with some variants performing better than others in their environment. Over time, beneficial variations accumulate, gradually transforming populations and eventually producing new species. This process operates regardless of the specific environment, whether in tropical rainforests, Arctic tundra, deep ocean trenches, or subterranean rock formations. The deep subsurface certainly provides all 3 necessary elements. Microorganisms that reproduce, mutations create variation, and differences in metabolism efficiency or stress tolerance affect survival. The process simply unfolds across vastly different timescales and under selection pressures completely unlike anything at the surface. The slow metabolic rates of deep subsurface microorganisms mean that evolutionary change proceeds at a similarly glacial pace. A bacterial species at the surface might experience thousands of generations per year, allowing rapid adaptation to changing conditions. A deep subsurface species, reproducing once per century, would require hundreds of thousands of years to achieve the same number of generations. This slow pace might seem to limit evolutionary potential, but it also provides advantages. Deep subsurface environments are remarkably stable compared to the surface. Temperature, pressure, and chemical composition change very slowly, if at all, over millions of years. Once a species becomes well adapted to these conditions, there is little selective pressure for further change. Populations can persist essentially unchanged for immense periods, becoming what biologists call living fossils, organisms that represent ancient lineages preserved by environmental stability. Some researchers have proposed that the deep biosphere might contain the oldest continuously existing life forms on Earth. While surface species have been repeatedly disrupted by climate changes, ice ages, asteroid impacts, and mass extinctions, deep subsurface populations remained buffered from these catastrophes, protected by miles of rock. The microorganisms living in fractures and pores today might be direct descendants, with minimal genetic change, of species that colonized these environments billions of years ago when Earth's surface was still hostile to most life forms. In this sense, the deep subsurface could serve as a biological archive, preserving ancient forms that evolved in Earth's early oceans and then retreated underground as surface conditions changed. Studying these organisms might provide insights into the nature of early life, before photosynthesis, before oxygen, when all organisms derived energy from chemicals and heat. Could evolution in deep subsurface environments produce multicellular organisms, creatures with differentiated tissues and organ systems? At first consideration, the answer seems negative. The energy available in these environments appears too limited to support complex metabolisms. Multicellular organisms require substantially more energy than single cells because they must maintain communication systems between cells, transport nutrients and waste products, and coordinate activity across their bodies. Surface ecosystems ultimately derive their energy from the sun, which provides abundant power for elaborate food webs and complex organisms. Deep subsurface energy sources, hydrogen from rock-water reactions, organic compounds from surface sources that percolate down over millennia, radioactive decay, seem insufficient to power anything beyond simple microbes. However, certain deep subsurface environments might offer more energy than the typical deep crustal habitat. Regions near magma chambers receive substantial heat, driving vigorous chemical reactions that could support more complex ecosystems. Fracture zones where water from different sources mixes might create chemical gradients that organisms could exploit, similar to how hydrothermal vent communities harvest energy from the mixing of hot, mineral-rich vent water with cold, oxygenated ocean water. Some theoretical models suggest that substantial cavities in the lower crust or upper mantle might contain pockets of water at high pressure and temperature, creating fluid-filled voids where dissolved gases and minerals could support chemosynthetic food webs of surprising complexity. In such environments, evolution might have had billions of years to produce organisms beyond the microbial scale. The discovery of macroscopic organisms in deep mines and caves demonstrates that complex multicellular life can colonize the deep subsurface, at least in regions connected to the surface. Cave-adapted fish, insects, crustaceans, and other invertebrates inhabit underground rivers and lakes worldwide, many showing remarkable adaptations to the eternal darkness. They typically lack pigmentation, becoming ghostly white or translucent. They lose their eyes entirely or retain only vestigial structures beneath the skin. They develop enhanced senses of touch, smell, and vibration detection to navigate and find food without vision. They often exhibit extremely slow metabolisms and growth rates, with some cave fish living for decades and requiring years to reach maturity. These organisms demonstrate that evolution can produce complex, multicellular life in perpetually dark environments, albeit in cases where energy ultimately derives from surface sources through underground water flows carrying organic matter from above. But what if isolated subsurface ecosystems existed with no connection to the surface, no input of organic matter from photosynthesis, operating entirely on geochemical energy? Could such systems support not just microbes, but entire food webs of progressively larger organisms? The hydrothermal vent communities in the deep ocean provide a possible model. At these vents, bacteria use hydrogen sulfide and other chemicals from volcanic activity to produce organic compounds through chemosynthesis. These bacteria form the base of a food web that includes tube worms up to 8 feet long, clams, mussels, shrimp, crabs, and fish. The entire ecosystem operates without any input from sunlight, deriving all its energy from Earth's internal heat and chemical processes. This ecosystem exists at the surface of the oceanic crust, but the principle could apply to isolated cavities at greater depths if conditions permitted sufficient chemical energy flow. Theoretical biologists have speculated about what deep subsurface organisms might look like if they evolved to larger scales. In the absence of vision, sensory systems would likely focus on detecting chemical gradients, vibrations, and possibly electrical or magnetic fields. Bodies might be optimized for moving through fluid-filled fractures or navigating through zones of varying pressure and temperature. Metabolism would necessarily be slow, requiring minimal energy input, with long lifespans and infrequent reproduction. Communication between individuals might occur through chemical signaling, acoustic frequencies transmitted through rock, or bioluminescence, though the latter seems unlikely if no organisms possess light detection abilities. Social behavior might be limited, as the low-energy environment could not support high population densities. But over billions of years of evolution in stable conditions, what might emerge from such constraints? One particularly intriguing possibility involves the evolution of intelligence in deep subsurface environments. Intelligence, broadly defined as the ability to process information about the environment and respond flexibly to achieve goals, provides survival advantages in complex or changing conditions. Deep subsurface environments might seem too simple and stable to favor intelligence. Why develop cognitive abilities if conditions never change and optimal strategies are fixed? However, intelligence also offers advantages in sparse environments where resources are scattered and unpredictable in their distribution. An organism that can learn, remember locations, and plan efficient foraging routes would outcompete one that searches randomly. If deep subsurface cavities contain scattered pockets of chemical energy, acoustic signaling systems for long-distance communication, or social structures that benefit from cooperation, selection might favor cognitive abilities despite the harsh conditions. The evolution of intelligence on Earth's surface followed a path from simple nervous systems toward increasingly complex brains capable of learning, memory, and abstract reasoning. This process required substantial energy investment, as nervous tissue is metabolically expensive, but provided advantages in foraging efficiency, predator avoidance, and social coordination. A similar process could theoretically occur in deep subsurface environments, though proceeding much more slowly due to energy constraints and slow reproduction rates. An intelligent deep subsurface organism might bear no resemblance to surface life. It might exist as a distributed network of interconnected nodes rather than a centralized brain. It might process information over timescales of years rather than milliseconds. It might lack individual bodies entirely, existing as a colony organism with specialized cells performing different functions. The possibilities expand when we abandon assumptions based on surface biology and consider what evolution might produce under radically different constraints. If organisms, perhaps even intelligent organisms, exist in Earth's deep interior, could we detect them? What signals might they produce? And would our instruments recognize these signals as evidence of life rather than dismissing them as geological noise? The challenge of detecting deep subsurface life becomes exponentially more difficult as depth increases. We can sample microorganisms from mines and boreholes, directly observing them and studying their biology. But anything existing beyond the reach of drilling, deeper than 7 or 8 miles in the crust, let alone in the mantle, remains accessible only through indirect detection methods. We must look for anomalies, patterns that do not match expectations for purely geological processes, and then attempt to determine whether these anomalies might indicate biological activity. Seismic monitoring provides one potential avenue for detection. Earthquakes and tectonic activity generate seismic waves that travel through the entire planet, and by analyzing these waves from multiple monitoring stations, seismologists can construct detailed models of Earth's internal structure. The speed at which seismic waves travel depends on the density, temperature, and composition of the material they pass through. Fluids transmit seismic waves differently than solid rock, allowing detection of underground water reservoirs, magma chambers, and pockets of oil or gas. Could biological structures produce detectable seismic anomalies? A large subsurface cavity containing water and potentially organic matter might show different seismic properties than surrounding rock. A network of passages or chambers might create distinctive echo patterns. However, distinguishing such signals from the countless natural variations in crustal structure remains extraordinarily difficult. Unusual seismic events have occasionally puzzled researchers. In 1997, underwater listening devices operated by the National Oceanic and Atmospheric Administration detected an extremely powerful, ultra-low frequency sound in the southern Pacific Ocean. The sound, dubbed the bloop, was loud enough to be detected by sensors thousands of miles apart, yet its source remained unidentified. Its frequency pattern matched the profile of a living creature, similar to calls produced by whales, but far louder than any known biological source could produce. Many speculated about an unknown species of enormous deep-sea creature. Eventually, researchers concluded that the bloop most likely resulted from an ice quake, the fracturing and movement of large icebergs in Antarctica. But the incident illustrates how acoustic anomalies can generate speculation about unknown life forms and how difficult it can be to definitively identify the source of unusual sounds. Similar acoustic mysteries occur in underground environments. Miners occasionally report unusual sounds, deep rumblings that do not correspond to blasting or equipment, resonant tones that seem to emanate from beyond the rock face, strange echoes in abandoned tunnels. Most such reports have mundane explanations: water moving through fractures, rocks settling under stress, thermal expansion and contraction, or simple acoustic illusions created by the peculiar properties of underground spaces. But some reports defy easy explanation, describing sounds with regular patterns, almost rhythmic qualities, or other characteristics that seem to suggest something beyond random geological processes. Could any of these represent biological sounds, creatures, or even civilizations communicating through rock-transmitted frequencies, their signals misinterpreted as seismic noise? Electromagnetic anomalies provide another potential signature of deep subsurface activity. Living organisms, particularly those with nervous systems, generate electrical fields as part of their normal function. Sharks and other predatory fish can detect the minute electrical fields produced by muscle contractions in hidden prey. The human brain generates electrical activity measurable by electroencephalography. A sufficiently large population of organisms, or a highly electrically active organism adapted to the deep subsurface, might produce detectable electromagnetic signatures. Earth's magnetic field undergoes constant fluctuations, some related to solar activity, some to movements in the molten outer core, and some to crustal magnetization. Could any of these fluctuations result from biological activity? The difficulty lies in distinguishing hypothetical biological signals from the overwhelming background of geological electromagnetic phenomena. Throughout the 20th century, researchers occasionally detected electromagnetic anomalies that defied conventional explanation. In the 1970s, Soviet scientists studying the Earth's magnetic field reported periodic variations that did not correlate with any known geological or solar process. These variations occurred at extremely low frequencies, below the range of human hearing but potentially detectable by specialized sensors. The patterns showed regularities that seemed inconsistent with random fluctuations, though never organized enough to suggest deliberate signaling. Western scientists who reviewed the data generally attributed the anomalies to measurement errors, equipment malfunctions, or simply complex interactions between crustal magnetization and thermal currents in the mantle. No consensus emerged on whether the observations represented anything genuinely unusual or merely reflected the limitations of 1970s detection equipment. More recent research has focused on studying electrical conductivity variations within the Earth's crust and mantle. Different minerals and rock types conduct electricity at different rates, allowing researchers to map subsurface structure by measuring how electrical currents propagate through the ground. These magnetotelluric surveys have revealed unexpected zones of high electrical conductivity at various depths, some of which do not match predictions based on known rock types and temperatures. Water and dissolved minerals increase conductivity, so these zones might indicate aquifers or pockets of mineral-rich fluid. But could they also indicate something else? Organic matter, particularly in concentrated forms, also conducts electricity differently than typical rock. A massive accumulation of biological material, perhaps the remains of ancient deep biosphere organisms or even living biomass, might create detectable conductivity anomalies. The challenge of signal detection becomes even more complex when we consider that any hypothetical deep subsurface civilization would have evolved under completely different conditions than surface life. Their communication methods, if they possessed any, would likely utilize media available in their environment. Sound travels well through solid rock and water, making acoustic signaling a logical choice. Chemical signaling, releasing and detecting specific molecules, would work in fluid-filled environments. Electromagnetic communication might be possible if organisms developed bioelectrical capabilities. But would we recognize any of these signals as communication rather than noise? Human language occupies a narrow range of frequencies and follows patterns shaped by our vocal apparatus, auditory system, and cognitive architecture. An entirely different form of intelligence, evolved in isolation, might communicate in ways completely opaque to us even if we detected their signals. The search for extraterrestrial intelligence, or SETI, faces similar challenges when listening for signals from alien civilizations. Radio telescopes scan the heavens for narrowband signals or organized patterns that would indicate technological activity rather than natural astronomical processes. But this search assumes that alien civilizations would use electromagnetic radiation for communication, and that their signals would have characteristics recognizable as artificial. If aliens communicated using neutrinos, gravitational waves, or some other medium we barely understand, our radio telescopes would miss them entirely. Similarly, a search for deep subsurface intelligence must confront the possibility that we might be looking for the wrong type of signal, using instruments designed to detect geological processes rather than biological activity. One intriguing avenue for investigation involves monitoring for biological molecules at greater depths than expected. When drilling projects or mining operations penetrate deep rock, chemical analysis of the samples can detect organic compounds, molecules containing carbon-hydrogen bonds that typically indicate biological activity. Most organic compounds found at depth result from ancient surface life, fossilized organisms, kerogen, and petroleum deposits representing concentrated biomass from prehistoric oceans and forests. But occasionally, analyses detect organic compounds with unusual isotopic signatures or molecular structures that do not match expected patterns from ancient surface life. These anomalies might indicate deep biosphere organisms with unique metabolisms, or they might simply reflect complex geochemical processes that can produce organic molecules without biological involvement. Distinguishing between these possibilities requires careful analysis and often remains inconclusive. In 2013, researchers studying fluid samples from a deep gold mine in South Africa, approximately 2 miles beneath the surface, discovered an isolated ecosystem dominated by a single bacterial species that survived entirely on hydrogen produced by radioactive decay in surrounding rock, with no energy input from the surface. The bacteria had apparently lived in complete isolation for millions of years, separated from all other life by impermeable rock layers. This discovery demonstrated that self-sustaining ecosystems could exist at significant depth, deriving energy entirely from geochemical sources. It also raised the question of how many other isolated ecosystems might exist in the deep crust, unknown to science, because we have not drilled in the right locations or at sufficient depths. Each such ecosystem represents an independent experiment in evolution, potentially producing unique organisms found nowhere else on Earth. The possibility of communication or interaction between surface and subsurface realms appears in numerous cultural traditions, though typically framed in mythological or religious terms. Ancient texts describe beings emerging from underground realms, possessing knowledge or abilities beyond those of surface dwellers. The Sumerian myths speak of the Anunnaki descending from the heavens, but also emerging from the Abzu, the primordial underground waters. Greek myths describe the Telchines, enigmatic beings associated with Rhodes and Crete, said to have emerged from the sea or from underground sources, possessing metallurgical knowledge and mystical powers. Native American traditions from the Hopi to the Cherokee describe emergence from previous worlds located underground, with certain caves and springs serving as portals between realms. While these myths clearly should not be taken as literal historical accounts, they reflect a persistent human intuition that something significant exists beneath the surface, something that occasionally intersects with the surface world. Could such intersections actually occur? If substantial caverns or ecosystems exist at depth, might there be pathways connecting them to the surface? Cave systems certainly demonstrate that vertical passages can extend miles into the crust, and submarine canyons show that seafloor topography can create dramatic depth variations. But a truly isolated deep biosphere, separated from surface conditions by miles of impermeable rock, would by definition lack connections to the surface. The moment a passage opened between a deep cavity and the surface, conditions in a cavity would begin changing as surface water, air, or organisms entered. Any ecosystem adapted to high pressure, high temperature, oxygen-free conditions would face catastrophic disruption. From this perspective, The deep biosphere must remain isolated to persist, making direct contact between surface and subsurface realms impossible. Yet certain geological features might permit limited exchange without catastrophic disruption. Hydrothermal systems, where heated groundwater circulates between depth and surface, create chemical gradients that organisms could exploit. Deep ocean vents demonstrate this principle, with organisms living in transition zones where deep geochemical environments meet surface ocean conditions. Continental hot springs show similar patterns, with microbial communities adapted to high-temperature environments, thriving in waters rising from deep aquifers. Could information, if not organisms themselves, travel along such pathways? Chemical signatures, dissolved gases, or even microscopic biological structures might be carried upward from depth, potentially providing evidence of deeper ecosystems to anyone examining these systems carefully. Throughout recorded history, various cultures have preserved accounts of encounters with beings or phenomena associated with the underworld. While mainstream scholarship interprets these as purely mythological, some researchers have wondered whether they might preserve distorted memories of genuine observations. The line between mythology, folklore, and historical record is often blurred, particularly in ancient sources where supernatural explanations mixed freely with factual accounts. Examining these texts with an open but critical perspective might reveal patterns worth investigating, even if the literal truth of the stories remains doubtful. The Buddhist cosmology describes Patala, a magnificent underworld divided into 7 layers descending beneath the surface. These layers are inhabited by the Nagas, serpent beings of great power and wisdom. The Nagas are described as guardians of treasures, both material and spiritual, dwelling in vast underground cities filled with jewels and advanced knowledge. While clearly mythological, the descriptions include specific details about underground architecture, light sources that function without fire, and technologies beyond surface civilization's capabilities. Some interpreters have suggested that these texts might preserve memories of actual encounters with unknown phenomena, later transformed through oral tradition into religious mythology. The challenge lies in separating possible factual kernels from layers of symbolic elaboration. Tibetan Buddhist traditions speak of Shambhala, a hidden kingdom located in a valley or beneath the surface, accessible only to those who have achieved certain spiritual attainments. The kingdom is described as possessing advanced spiritual and technological development, with inhabitants living in harmony and wisdom far beyond surface humanity. Various expeditions throughout the 20th century attempted to locate Shambhala, searching remote Himalayan regions, caves, and valleys. None found conclusive evidence, leading most scholars to conclude that Shambhala exists purely as a spiritual metaphor for enlightenment rather than a physical location. Yet the persistence and specificity of the descriptions, across multiple texts and traditions, continue to fascinate those inclined toward alternative interpretations. Similar traditions exist in Hindu mythology, which describes multiple underworld realms called lokas, each with distinct characteristics and inhabitants. The Padala Loka, the lowest of these realms, is described as more beautiful and luxurious than the heavenly realms above, filled with jewels, pleasant temperatures despite being underground, and inhabitants who enjoy sensual pleasures unknown to surface dwellers. The Nagas rule these realms, possessing great wealth and magical powers. Ancient texts provide detailed descriptions of underground cities with crystal walls, self-illuminating gemstones providing light, and architecture more advanced than surface construction. Again, mainstream scholarship interprets these as purely mythological constructs, but the specificity of certain details, such as descriptions of temperature regulation, light sources, and architectural techniques, seems unusually elaborate for pure invention. Islamic tradition preserves stories of the jinn, beings created from smokeless fire who inhabit a realm parallel to the human world, often described as existing underground or in remote, inaccessible places. Certain types of jinn are specifically associated with caves, wells, and underground spaces. Medieval Islamic scholars debated the nature of jinn, with some treating them as purely spiritual beings and others suggesting they might be a different form of physical creature with unusual properties. Accounts of encounters with jinn in caves and underground spaces appear in various historical chronicles, though always filtered through theological and cultural interpretations that make factual assessment impossible. European folklore contains numerous traditions of underground dwellers. Celtic mythology describes the city, often identified with ancient barrows and underground chambers. Norse mythology places the dark elves Svartalfar in subterranean realms, contrasting with light elves who inhabit the sky. Germanic traditions describe dwarves living in vast underground kingdoms, mining precious metals, and creating magical artifacts with metallurgical skills surpassing human capabilities. These beings are typically described as shorter than humans, adapted to underground existence, and possessing knowledge of earth sciences and metalworking that humans lack. While clearly folkloric, these traditions appear across multiple cultures with similar characteristics, suggesting either common psychological archetypes or possibly cultural diffusion of stories based on unknown original sources. The Hollow Earth theory that gained prominence in the 19th and early 20th centuries drew partly on these mythological traditions, attempting to create a scientific framework that would validate ancient stories of underground civilizations. Admiral Richard Byrd's Antarctic expeditions in the 1940s became entangled with Hollow Earth claims when proponents alleged that Byrd had discovered openings to interior realms and that his reports were suppressed by authorities. Byrd's actual expedition logs and published accounts contain no such claims, but the myth persisted, enhanced by Cold War paranoia about secret government knowledge. Similar stories circulated about Nazi expeditions supposedly seeking underground realms in Antarctica, Tibet, or beneath the Andes. These claims lack credible evidence, but demonstrate the enduring appeal of the idea that something hidden exists beneath the surface. More contemporary accounts occasionally surface from individuals claiming unusual experiences in caves or mines. These reports typically describe encountering inexplicable sounds, lights without apparent sources, zones of unusual temperature or electromagnetic effects, or even glimpses of creatures unlike any known species. Most such accounts come from amateur explorers, making verification difficult. The few cases involving professional geologists or mining engineers typically result in conventional explanations being found for the anomalies. However, a small number of well-documented cases describe observations that remain unexplained even after thorough investigation. In 1995, a team of geologists exploring caves in the Muval region of Romania discovered a sealed underground ecosystem that had been isolated from the surface for approximately 5 million years. The cave atmosphere contained high levels of hydrogen sulfide and carbon dioxide, but very little oxygen, conditions lethal to most surface organisms. Yet the cave harbored over 30 species of invertebrates, including spiders, scorpions, and various arthropods, all adapted to the toxic atmosphere and complete darkness. These species existed nowhere else on Earth, having evolved in isolation for millions of years. The discovery demonstrated conclusively that Earth's subsurface contains biological complexity far beyond what was previously imagined, and that ecosystems can persist in complete isolation from surface conditions for geological timescales. The Muval Cave ecosystem derives its energy from chemosynthetic bacteria that metabolize hydrogen sulfide and other chemicals rising from deeper geological sources. These bacteria form mats on the cave walls and in the underground lakes, serving as the base of a food web supporting the cave's diverse fauna. The entire system operates without any input from photosynthesis or the surface world, powered entirely by geochemical processes. This discovery validated theories about chemosynthetic ecosystems in a deep subsurface and provided a concrete example of how life could exist in isolated underground environments. It also raised the question of how many similar sealed caves or deeper cavities might exist worldwide, each potentially harboring unique biological communities. The exploration of lava tubes, caves formed by flowing lava during volcanic eruptions, has revealed that these features can extend for miles beneath the surface and often connect to larger chambers of unknown extent. In 2017, satellite data analysis suggested that a lava tube beneath the lunar surface near the Marius Hills region could be large enough to contain a major city. If such vast voids exist on the airless, geologically inactive moon, what might exist within Earth's far more active and water-rich crust? Lava tubes on Earth have been mapped to depths exceeding a mile, but most explorations encounter obstacles, collapsed sections, flooded passages, or simply the limitations of available equipment before reaching the tube's full extent. Remote sensing suggests that some tubes continue much deeper, potentially connecting to magma chamber regions or intersecting with other cavity systems. As we conclude this part of our journey deeper into the mysteries beneath our world, we would like to extend a special thank you for continuing with us. If these explorations of hidden realms and ancient wisdom are bringing you comfort, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It is always fascinating to connect with our global community of curious minds who ponder these profound mysteries. You can also share which theories or discoveries have resonated most strongly with you. It would be wonderful to hear your thoughts. Now, let these revelations of isolated ecosystems and persistent myths settle into your consciousness as we prepare for the final part of our exploration, where we will consider what all of this might mean for humanity's understanding of our planet and our place within it. The question of whether advanced life exists in Earth's subsurface cannot be answered through speculation alone. If the hypothesis has any validity, it must be testable through observation, experimentation, and systematic investigation. Throughout the latter half of the 20th century and into the 21st, various scientific disciplines have developed technologies that permit increasingly sophisticated examination of Earth's interior. While direct access remains limited to the upper few miles of the crust, indirect methods have revolutionized our understanding of what lies beneath. Each technological advance brings new data, sometimes confirming conventional models, occasionally revealing anomalies that challenge assumptions and require explanation. Deep ocean exploration represents one of the most promising frontiers for discovering subsurface life. The ocean floor remains less thoroughly mapped than the surface of Mars or the Moon. Vast regions have never been observed directly, surveyed only with low-resolution sonar that can detect major topographic features, but misses smaller structures entirely. Where detailed exploration has occurred, it has repeatedly revealed unexpected biological communities and geological features. The discovery of hydrothermal vents in 1977 overturned the assumption that deep ocean floors were biological deserts. If such fundamental discoveries can occur in environments we considered well understood, what might exist in regions we have never explored? Submarine caves represent particularly intriguing targets for investigation. Unlike terrestrial caves, which have been systematically explored by generations of spelunkers, submarine caves present enormous technical challenges. Accessing them requires specialized diving equipment capable of operating at extreme depths and pressures. Many extend horizontally into the oceanic crust or continental shelves, reaching depths impossible for human divers. Remotely operated vehicles can explore further, but their mobility is limited, and they provide only visual and basic chemical data. Despite these limitations, exploration of submarine caves has revealed ecosystems adapted to perpetual darkness and unusual chemistry, including species found nowhere else on Earth. The oceanic crust itself differs substantially from continental crust in ways that might favor the existence of larger subsurface cavities. Oceanic crust is thinner, typically only 3 to 6 miles thick compared to 20 to 45 miles for continental crust. It forms at mid-ocean ridges where magma rises from the mantle, creating new crust that then spreads outward. This formation process creates fractures, fissures, and void spaces that can become pathways for water circulation. Seawater percolates into the oceanic crust through these fractures, becomes heated by proximity to magma chambers, and rises back toward the seafloor through hydrothermal vents. This circulation system essentially means that significant volumes of the oceanic crust are not solid rock but rather fractured, fluid-filled zones where conditions might support extensive biological communities. Recent research has revealed that the volume of oceanic crust harboring microbial life may far exceed previous estimates. A 2020 study analyzing samples from multiple ocean drilling projects concluded that living microorganisms exist throughout the entire thickness of the oceanic crust and possibly into the uppermost mantle beneath it. These organisms survive in fractures and pores at temperatures up to approximately 250 degrees Fahrenheit, near the theoretical limit for life as we understand it. The total biomass of this oceanic crustal biosphere may equal or exceed all life in the oceans above. This vast, hidden realm of life exists in a three-dimensional matrix extending beneath the entire ocean floor, a global ecosystem more extensive than the Amazon rainforest, but completely invisible from the surface. If microbial life exists throughout the oceanic crust, could more complex organisms inhabit larger cavities within it? The energy available from hydrothermal circulation might support more than just bacteria. Where fractures create larger voids and hydrothermal fluids mix with seawater, conditions might permit the evolution of multicellular organisms adapted to these unusual environments. These organisms would face extreme challenges: high pressure, complete darkness, temperatures near the upper limit of biological function, and severe energy limitations. But evolution has repeatedly demonstrated its ability to adapt life to seemingly impossible conditions. The question is not whether such adaptation is possible in principle, but whether it has actually occurred in Earth's history. One theoretical possibility that has gained attention among astrobiologists is the concept of a shadow biosphere, a second tree of life on Earth, descended from a separate origin event, potentially thriving in environments where conventional life cannot compete. Most research on Earth's early history assumes that all life descends from a single common ancestor that emerged around 4 billion years ago. But conditions on early Earth might have permitted multiple independent origins of life, with only one lineage ultimately dominating surface environments. Other lineages might have retreated to marginal environments where their different biochemistry provided advantages. The deep subsurface, with its exotic chemistry and isolation from surface conditions, represents exactly the type of environment where a shadow biosphere might persist, undetected because researchers are looking for familiar biochemical signatures rather than radically different forms of life. Searching for a shadow biosphere requires rethinking how we identify life itself. Current methods for detecting microorganisms rely on finding familiar molecules, DNA, RNA, proteins, lipids, and observing familiar metabolic processes. But if a shadow biosphere uses different information molecules, different metabolic pathways, or different cellular structures, these detection methods might fail to recognize it even when it is present in samples. Distinguishing between complex but non-living chemical processes and genuinely alternative biochemistry presents enormous challenges. Several research teams are developing new approaches that look for patterns of chemical organization, energy flow, and information processing rather than specific molecules, hoping to detect life regardless of its biochemical details. The exploration of extreme environments on Earth serves partly as preparation for the search for life elsewhere in the solar system. Mars, Europa, Enceladus, and other worlds may harbor subsurface oceans or deep aquifers where conditions resemble Earth's deep biosphere. The organisms we discover in Earth's subsurface provide models for what extraterrestrial life might resemble and demonstrate which conditions can support biology. If life can thrive miles beneath Earth's surface, in hot, pressurized, chemically exotic environments, then the potentially habitable volume of other planets and moons expands dramatically. We need not limit our search to surface waters or atmospheres, but should consider entire planetary crusts and mantles as potential habitats. This perspective transforms our understanding of Earth itself. Rather than a planet with a thin living skin covering an inert interior, Earth becomes a living world throughout its volume, with ecosystems extending from the atmosphere down through the crust and possibly into the upper mantle. The boundary between living and non-living becomes less distinct when we consider that the geochemical processes supporting the deep biosphere are themselves influenced by biological activity. Microorganisms alter the chemistry of their environment, changing mineral compositions, producing gases, and affecting how water and energy move through rock. Over geological time, the cumulative effects of the deep biosphere may have substantially altered Earth's interior structure and chemistry. Some researchers have proposed that life might not merely inhabit the deep Earth, but might have originated there. The surface of early Earth was hostile, bombarded by asteroids, flooded with intense ultraviolet radiation, subject to extreme temperature fluctuations. The subsurface provided protection, stable temperatures, and abundant chemical energy from hydrothermal systems. Life might have emerged in fractures within the oceanic crust or around deep hydrothermal systems, only later colonizing the surface once conditions improved. If this hypothesis is correct, then subsurface life is not a curiosity colonizing marginal environments, but represents the original form of terrestrial biology, with surface life being the adapted offshoot. The deep biosphere would be the parent lineage, preserving forms and metabolisms from Earth's earliest days. The possibility of intelligent life in Earth's deep interior requires addressing a fundamental question. What is intelligence, and what forms might it take under radically different conditions? Human intelligence evolved to solve problems specific to surface-dwelling, social primates, identifying food sources, navigating complex terrain, communicating with group members, predicting others' behavior, and transmitting cultural knowledge across generations. These selection pressures shaped our particular form of cognition, with its emphasis on visual processing, language, and abstract reasoning. But intelligence itself, defined broadly as the capacity to process information and adapt behavior to achieve goals, can take many forms depending on environmental pressures and evolutionary history. On Earth's surface, intelligence evolved multiple times in different lineages. Octopuses developed sophisticated problem-solving abilities despite having nervous systems organized completely differently from vertebrates. Their intelligence is distributed throughout their arms, each of which can process information semi-independently. Corvids, crows, and ravens demonstrate reasoning, tool use, and future planning despite having brains structured differently from mammals. dolphins and whales developed complex communication and social learning despite living in a three-dimensional aquatic environment. These examples demonstrate that intelligence can emerge from diverse neural architectures in varied environments. Could intelligence emerge in the deep subsurface, shaped by selection pressures we can barely imagine? The challenges of deep subsurface existence might favor certain cognitive abilities. In an environment where resources are scattered and irregularly distributed, spatial memory and route planning would provide enormous advantages. An organism that could remember the locations of chemically rich zones, navigate efficiently through complex three-dimensional fracture systems, and optimize foraging paths would outcompete those searching randomly. If multiple individuals could share information about resource locations, cooperation and communication would become valuable, potentially driving the evolution of increasingly sophisticated signaling systems. Over geological timescales, these selection pressures might gradually favor larger nervous systems capable of more complex processing, ultimately producing what we would recognize as intelligence. The time frame available for such evolution is essentially unlimited. Microbial life may have colonized the deep subsurface within a few 100 million years of Earth's formation, approximately 4 billion years ago. Surface life took roughly 3.5 billion years to evolve from bacteria to primates. If deep subsurface evolution proceeded at even a fraction of that pace, there has been time for complex organisms and possibly intelligence to emerge. The slower metabolic rates and longer generation times of subsurface organisms would slow evolution compared to surface rates, but the stability of deep environments might compensate by providing consistent selective pressures over enormous periods. A lineage experiencing one generation per century would still accumulate 40 million generations over 4 billion years, more than enough for substantial evolutionary change. But would intelligence arising in such an environment resemble anything we would recognize? Human consciousness emerges from electrochemical signaling between billions of neurons, operating at millisecond timescales, processing sensory information about a world of light, sound, touch, taste, and smell. A hypothetical deep subsurface intelligence might operate on entirely different principles. It might process information through chemical rather than electrical signaling, with thoughts occurring over hours or days rather than seconds. It might lack discrete sensory organs, instead directly detecting chemical gradients, pressure variations, and thermal flows throughout its body or environment. Its subjective experience might be so alien that the term consciousness becomes questionable, yet it might still possess the capacity for memory, learning, goal-directed behavior, and perhaps even abstract reasoning. One particularly speculative possibility involves distributed or collective intelligence. On the surface, most intelligent organisms are individuals with centralized nervous systems. But the deep biosphere includes extensive microbial mats and biofilms, communities of microorganisms living in close association, communicating through chemical signals, and sometimes exchanging genetic material. Could such a community develop a form of collective information processing that functions as a distributed intelligence? Individual microorganisms would serve roles similar to neurons, each responding to local conditions and communicating with neighbors, with complex behavior emerging from the interactions of countless simple units. Such a system might lack consciousness in any sense we would recognize, but could still exhibit sophisticated adaptive behavior, learning, and memory distributed across the entire community. The concept of Gaia, proposed by scientist James Lovelock, suggests that Earth's biosphere functions as a self-regulating system maintaining conditions suitable for life. While Lovelock did not propose that Gaia is literally conscious or intelligent, some interpreters have wondered whether the cumulative feedback loops between life and environment might constitute a form of planetary cognition. The deep biosphere, extending throughout Earth's crust and interacting with geochemical processes over geological timescales, might play a crucial role in these feedback systems. If the entire deep biosphere functions as an interconnected system, with information flowing through chemical and perhaps electromagnetic channels, might it possess some form of collective awareness of Earth's internal state? These speculations venture far beyond current science into philosophical territory, but they serve a useful purpose in expanding our conception of what intelligence and consciousness might be. If we ever do detect evidence of complex subsurface life, we may face the challenge of determining whether it is intelligent without being able to apply familiar criteria like tool use, language, or cultural transmission. We might need new definitions of intelligence that focus on information processing, adaptive behavior, and system complexity rather than specific behaviors that happen to evolve in surface environments. The deep subsurface might host forms of cognition fundamentally different from anything in our experience, yet deserving of recognition as intelligent systems. The ethical implications of discovering intelligent life in Earth's interior would be profound. Humanity has generally treated the subsurface as a resource to be exploited, drilling for oil, mining for minerals, extracting groundwater, disposing of waste. If the deep Earth harbors not merely microbial ecosystems, but complex, possibly intelligent life, our activities might be inadvertently disrupting or destroying civilizations that have existed for millions of years. Deep geothermal drilling projects, radioactive waste repositories, hydraulic fracturing operations, and other activities that penetrate miles into the crust could potentially impact deep biosphere communities. Without awareness of their existence, we cannot assess or mitigate these impacts. Moreover, the discovery of terrestrial non-human intelligence would revolutionize our understanding of consciousness itself. All intelligent species we know about evolved on Earth's surface under similar conditions, providing limited basis for understanding intelligence in principle. A deep subsurface intelligence would offer a comparison case, allowing us to distinguish universal features of intelligence from those specific to surface environments. It might help us recognize intelligence when we encounter it elsewhere in the universe, and it might reveal aspects of cognition and consciousness that surface-dwelling intelligences cannot access or imagine. The philosophical implications would rival those of discovering extraterrestrial intelligence, and indeed, finding a truly alien intelligence within our own planet might be even more unsettling than finding one among the stars. As our exploration of the hidden realms beneath our feet draws toward its conclusion, we find ourselves confronting questions that extend far beyond geology or biology into the realm of human meaning and cosmic significance. The possibility that our planet harbors unknown worlds within its depths challenges our sense of knowing our own home, of having thoroughly explored and categorized the Earth we walk upon. It suggests that mystery and wonder need not be sought in distant galaxies or quantum dimensions, but may exist just beyond the reach of our deepest mines and boreholes, separated from us by near miles of rock, yet as inaccessible as the most remote stars. The history of exploration demonstrates that humans consistently underestimate how much remains undiscovered. At every stage, explorers and scientists have believed they were nearing complete knowledge of Earth's surface, only to find vast regions previously unknown. The Pacific Ocean was entirely unmapped by Europeans until the 16th century, despite covering a third of Earth's surface. Antarctica remained undiscovered until 1820. The Amazon basin contained indigenous civilizations of substantial complexity that remained unknown to outside world until the 20th century. Even today, new species are discovered annually, and large animals previously thought extinct occasionally reappear. If the surface world, accessible to direct observation, contains so many mysteries, How much more mysterious must be the subsurface, accessible only through limited drill holes and indirect sensing? The deep biosphere's discovery in the late 20th century demonstrated that our ignorance of Earth's interior was even more profound than suspected. Before the 1980s, most scientists assumed that life existed only in a thin layer at the surface, dependent on photosynthesis. The realization that immense volumes of living biomass exist miles beneath the surface, following metabolisms completely different from surface ecosystems, forced a fundamental reconceptualization of the biosphere's extent and nature. This discovery came not through theoretical prediction but through direct sampling. Scientists drilled in locations they expected to be sterile and found thriving microbial communities instead. What other assumptions about the subsurface might prove equally wrong when we finally develop technologies to explore more deeply and comprehensively? The practical barriers to deep Earth exploration remain formidable. The Kolas super-deep borehole required 2 decades of continuous effort and ultimately failed to penetrate even halfway through the crust due to extreme heat and pressure. Current technology cannot drill substantially deeper without revolutionary advances in materials science and engineering. Manned exploration is even more challenging. No technology exists or is foreseeable that would allow humans to descend more than a few miles into the solid crust. Even unmanned probes face severe limitations. The pressure at the boundary between crust and mantle exceeds 130,000 times atmospheric pressure at sea level, and temperatures exceed 1,800 degrees Fahrenheit. Materials that can function in such conditions while also containing sensors and communication systems do not currently exist. Yet indirect methods continue improving. Seismology has reached the point where detailed three-dimensional models of Earth's interior can be constructed, revealing structure at resolutions of just a few miles. Neutrino detectors can observe the composition of Earth's core by measuring particles that pass through the entire planet. Gravimetric surveys can detect density variations in the crust with increasing precision. Each advance in detection technology provides new opportunities to identify anomalies that might indicate biological activity or unexpected structures. The challenge lies in distinguishing genuine anomalies from the countless natural variations in crustal composition, temperature, and density. The search for deep subsurface life connects to broader questions about life's distribution throughout the universe. If life can exist miles beneath Earth's surface, in hot, high-pressure, chemically extreme environments powered by geochemical rather than solar energy, then the potentially habitable volume of the universe expands enormously. Most planets and moons lack substantial atmospheres or surface liquid water, but many possess differentiated interiors with heat from radioactive decay and possibly subsurface water. Mars, Europa, Enceladus, Titan, and numerous other bodies in our solar system alone might harbor subsurface biospheres similar to Earth's deep subsurface communities. The search for life elsewhere increasingly focuses on these subsurface environments rather than surface conditions. This perspective suggests a universe where life is common but hidden, thriving in the interiors of planets and moons where conditions remain stable over billions of years while surfaces undergo dramatic changes. Earth's own history supports this view. The surface has experienced multiple mass extinctions, ice ages, asteroid impacts, and atmospheric transformations that would have devastated any surface-dependent biosphere. Yet life persisted, possibly because robust populations existed in the deep subsurface, buffered from surface catastrophes by miles of protective rock. When surface conditions eventually improved, subsurface life could have recolonized the surface, maintaining biodiversity across geological upheavals. The cultural and psychological significance of the hollow or inhabited Earth concept deserves consideration beyond its scientific validity. Humans have always been drawn to mysteries, to the possibility that more exists than what we can directly observe. The appeal of underground civilizations, hidden kingdoms, and secret realms beneath our feet speaks to something deep in human imagination, perhaps the recognition that consciousness itself is hidden, emerging from electrochemical processes we cannot directly observe, or perhaps simply the eternal human desire to believe that mystery persists, that complete knowledge remains forever just beyond reach. In an age where satellite imagery has mapped every square mile of Earth's surface, where few blank spaces remain on maps, the subsurface represents one of the last true frontiers, genuinely unknown and perhaps eternally unknowable in its deepest reaches. The scientific investigation of deep Earth has philosophical implications that extend beyond the specific question of subsurface life. It challenges anthropocentric assumptions about what matters and what deserves study. For most of history, science focused on phenomena directly relevant to human experience: the visible sky, the habitable surface, the organisms we encounter daily. The deep subsurface offers nothing of direct practical value to surface dwellers. We cannot live there, cannot extract resources efficiently from great depths, cannot use it for agriculture or habitation. Yet studying it expands our understanding of life's possibilities, planetary processes, and the nature of our world. It represents science pursued purely for knowledge, for the satisfaction of answering fundamental questions about reality, regardless of immediate application. As we contemplate the possibility of civilizations existing miles beneath our feet, evolved in darkness and pressure, perhaps possessed of intelligence we would not recognize, we might reflect on the limitations of human perception and understanding. We experience reality through narrow sensory windows, visible light representing a tiny fraction of the electromagnetic spectrum, sounds between 20 Hz and 20 kHz when the universe vibrates at frequencies from 0 to infinity, temperatures between approximately -40 and 120 degrees Fahrenheit when the cosmos ranges from absolute zero to the centers of stars. Entire categories of phenomena might exist that we simply cannot perceive without instruments. If intelligence evolved in an environment completely different from ours, it might be aware of aspects of reality we cannot access, while remaining ignorant of things we take for granted. The deep Earth, if it harbors life, remains indifferent to our speculation. Whatever exists there has persisted for millions or billions of years without contact with surface life, following its own evolutionary path, adapted to its own conditions. Our discovery of it, should that occur, would be momentous for us but might mean nothing to deep subsurface organisms lacking any concept of a surface world. They would be as alien to us as any extraterrestrial life, yet they would be terrestrial, having evolved on the same planet, sharing the same ultimate origin in Earth's primordial chemistry. This paradox captures something essential about the nature of life and intelligence, that isolation and adaptation can create unbridgeable gaps even between organisms sharing a planet, that the conditions of existence shape not just bodies but minds, perceptions, and the very categories through which we understand reality. The journey we have undertaken together through these layers of evidence, speculation, and wonder brings us finally to a place of productive uncertainty. We cannot definitively prove that advanced life exists in Earth's deep interior, but neither can we rule it out. The evidence suggests that the subsurface is far more complex, far more alive, and far more mysterious than previously imagined. Vast aquifers flow through crustal fractures. Enormous caverns exist at depths we can barely explore. Microbial ecosystems thrive in conditions once thought utterly incompatible with biology. Ancient isolated environments preserve unique life forms found nowhere else. And beyond the reach of our current technology, in the vast volumes of Earth's deeper crust and upper mantle, conditions exist that we can only model theoretically, never directly observe. Perhaps the most important insight emerging from our exploration is not about what exists beneath our feet, but about the nature of mystery itself. In our modern age, we are accustomed to information being readily available, to questions being answerable through quick searches and expert consultation. The deep earth reminds us that fundamental mysteries persist, that enormous aspects of reality remain genuinely unknown despite centuries of scientific progress. This is not a failure of science, but a reflection of the universe's vastness and complexity. Some questions may remain unanswered for generations, awaiting technological advances we cannot yet envision. Others may prove permanently beyond our reach, too distant, too extreme, or too different from our frame of reference to ever be fully understood. There is something deeply comforting about this persistent mystery, particularly as we settle into rest and allow our thoughts to drift. The earth beneath us is not simply a ball of rock and metal, predictable and fully mapped, but a dynamic, living, mysterious world extending far beyond our direct experience. Every moment, as we sleep or wake, immense volumes of water flow through crustal aquifers. Microorganisms divide in fractures miles beneath the ocean floor, continuing lineages billions of years old. Heat from radioactive decay warms pockets of ancient water trapped since Earth's formation. Minerals gradually dissolve and recrystallize in patterns shaped by pressure, temperature, and time. And perhaps, in cavities we have never detected, in conditions we can barely imagine, other forms of existence persist, following their own timelines, pursuing their own imperatives, completely unaware of the surface world and its inhabitants. This vision of Earth as a layered mystery, with known surfaces giving way to partially explored depths and, finally, to completely unknown realms, mirrors the structure of consciousness itself. We know our immediate thoughts and sensations, the content of present awareness. We have partial access to memories and subconscious processes through introspection and dreams. But deeper layers of mental activity, the neural mechanisms underlying thought, the processing occurring beneath conscious awareness, the vast biological operations maintaining our bodies moment by moment, remain as hidden from direct experience as the deep subsurface. We are, each of us, mysteries to ourselves, walking mysteries upon a mysterious world, surrounded by other mysterious consciousnesses, all of us afloat in a universe whose ultimate nature and extent remain unknown despite millennia of questioning. The ancient traditions that spoke of underworld realms, of beings dwelling beneath the surface, of hidden kingdoms and secret wisdom preserved in the depths, may have been expressing this intuitive understanding in mythological language. They recognize that the world contains more than what appears on the surface, that depth exists both literally and metaphorically, that the fully known and mapped world is an illusion. Modern science has confirmed this intuition in unexpected ways, revealing that Earth's interior hosts vast ecosystems, that the deep subsurface teems with life, that caverns of cathedral proportions exist in the crust, that water oceans dwarf surface seas. The myths were wrong in their specific claims, but right in their essential insight. Beneath the familiar world lies another world, different in kind, following different rules, yet intimately connected to the surface realm we inhabit. As you rest now, in whatever place you have made comfortable, at whatever hour of the day or night, consider the ground beneath you. Whether you lie in a bed on the 10th floor of an apartment building or on the ground floor of a house, beneath the foundation, beneath the soil and concrete, beneath the topsoil and bedrock, layers upon layers extend downward. A mile beneath you, rock exists that has never known sunlight, that has remained in darkness since its formation hundreds of millions of years ago. 2 miles down, temperatures approach the boiling point of water, yet ancient fluids circulate through fractures, carrying dissolved minerals and perhaps harboring microbial life. 5 miles below, at the deepest reach of human drilling, the rock becomes too hot and pressurized for conventional sampling, and everything below that depth remains known only through indirect inference. And somewhere in those unimaginable depths, in conditions we can barely model and cannot directly observe, what exists? We do not know. We may never know. But the question itself has value, opening our imagination to possibilities beyond the everyday, reminding us that for all our knowledge and technology, we remain barely acquainted with our own planet. The Earth keeps its deepest secrets still, and perhaps some secrets are meant to be kept, preserving mystery and wonder in a world that often seems too thoroughly explained, too completely understood, too lacking in genuine frontiers. The search for life in Earth's interior, whether microbial or complex, whether simple organisms or advanced intelligences, represents more than scientific curiosity. It embodies the human impulse to explore, to question, to reach beyond the comfortable and familiar into the unknown. Every major expansion of human knowledge has come from willingness to challenge assumptions, to look in places others dismissed as impossible or irrelevant, to take seriously ideas that seemed absurd from conventional perspectives. The hollow Earth theories of past centuries were wrong in their specifics, but they kept alive the question of what lies beneath, maintaining attention on the subsurface until technology advanced enough to begin genuine exploration. Today's investigations into the deep biosphere, into subsurface cavities and aquifers, into the possibilities of complex subterranean life, continue this tradition of questioning and exploring. Perhaps future generations will develop technologies that allow comprehensive exploration of Earth's interior, mapping every cavity, sampling every environment, determining conclusively what life exists at each depth. Or perhaps the deep Earth will remain forever partially inaccessible, its deepest zones too extreme for any probe we can devise, preserving a pocket of mystery at the heart of our world. Either outcome has its own beauty. Complete knowledge would be satisfying, answering questions humans have pondered for millennia. Eternal mystery would be humbling, maintaining perspective on the limits of understanding, ensuring that wonder never completely yields to explanation. For now, in this present moment, the question remains open. Beneath our feet, beyond our sight, beneath oceans and continents, beneath mountains and plains, the deep Earth exists in its ancient patience. Microorganisms, we have confirmed, thrive in fractured rock miles below the surface, following metabolisms unchanged for billions of years. Vast caverns wait in darkness, some perhaps containing ecosystems we have not yet discovered. Aquifers flow through channels we have never mapped, carrying water isolated from the surface world for millions of years. And deeper still, beyond current exploration, the bulk of Earth's interior remains as unknown as it was to our distant ancestors who first wondered what lay beneath the ground. This is where our journey concludes, though the mystery continues. We have explored the evidence for life beneath our world, examined the discovery of the deep biosphere, considered vast subsurface cavities, and the possibility of complex organisms adapted to extreme depths. We have reviewed ancient traditions of underworld civilizations and modern discoveries that give those myths unexpected resonance. We have contemplated what intelligence might mean in environments completely unlike the surface, and considered the philosophical implications of discovering non-human intelligence within our own planet. The answers remain uncertain, but the questions have led us to a deeper appreciation of Earth's complexity and the persistent mysteries that make existence endlessly fascinating. As you drift towards sleep now, let your awareness settle like sediment in still water. The day's thoughts and concerns can dissolve, becoming less distinct, less urgent, slowly fading into the background. Your breathing deepens and slows, following its own ancient rhythm, the same rhythm that has sustained life since the first organisms emerged billions of years ago. Your body rests, releasing tension, trusting in the ground beneath you, that same ground that extends downward through layers we have explored together tonight in imagination and speculation. The deep earth continues its patient existence, indifferent to our awareness of it, following processes that span geological time. Water moves through stone at rates measured in centuries per mile. Microorganisms divide, perhaps once in a human lifetime. Mineral crystals grow atom by atom over millions of years. And somewhere in those timeless depths, perhaps other forms of existence follow their own incomprehensible rhythms, as far beyond our understanding as we would be beyond theirs. All of this unfolds continuously beneath the surface drama of human life, beneath history and civilization, beneath all the urgency and noise of the surface world. Let that perspective bring a sense of peace. Your concerns, while real and important in their own context, are brief ripples on an ocean of time. The Earth has turned for billions of years and will continue turning for billions more. Life has persisted through 5 major mass extinctions and will likely persist through whatever challenges lie ahead. The deep biosphere, isolated from surface catastrophes by miles of rock, maintains its vigil in the eternal darkness, preserving biological processes that connect directly to Earth's earliest days. You are part of this immense story, this ongoing experiment in complexity and consciousness that began in primordial seas or perhaps in deep hydrothermal vents and has branched and diversified into the incredible variety of forms we see around us, and perhaps into forms we never see, hidden in the unreachable depths. Sleep now, if sleep comes to you, or simply rest in comfortable stillness. Let your thoughts wander where they will, perhaps imagining caverns vast enough to contain cities, perhaps considering the microorganisms thriving in crushed rock 5 miles down, perhaps wondering what tomorrow's discoveries might reveal about our mysterious planet. Or let your thoughts dissolve entirely, allowing consciousness to settle into that peaceful state between waking and dreaming where the boundaries between self and world become less distinct, where you are simultaneously the aware observer and part of the observed world, a temporary organization of matter and energy that somehow became capable of wondering about its own nature and context. The mystery beneath our feet remains, patient and profound, waiting for future explorers, future technologies, future insights. But for tonight, for this moment, it is enough to have contemplated it together, to have descended in imagination through layers of rock and time, to have encountered the surprising reality of the deep biosphere and the tantalizing possibility of something more, something we have not yet imagined or discovered. The journey has taken us from Plato's descriptions of Atlantis to modern seismology, from ancient myths of underworld kingdoms to the discovery of microorganisms living in solid rock, from speculation about hollow Earth to the confirmed existence of caverns larger than cathedrals and aquifers vaster than surface oceans. We end where we began, standing on the surface of a mysterious world, but now with a deeper appreciation of how much lies beneath the familiar ground. Every step you take, you walk above worlds within worlds, layers of complexity extending far beyond sight or direct experience. And in that recognition, perhaps there is comfort, the comfort of knowing that mystery persists, that not everything is known or knowable, that the universe retains its capacity to surprise and astonish us. We are explorers on an incompletely explored world, conscious beings contemplating the possibility of other consciousness evolved under unimaginably different conditions, temporary patterns of organization wondering about our place in the vast, patient, mysterious earth that holds us. Rest well in this knowledge. Let it settle into your awareness like sediment through water, slowly, gently, becoming part of your understanding. The deep earth continues its ancient existence, and you continue yours, both part of the same planetary story, the same unfolding experiment in complexity that has been proceeding for 4.5 billion years and shows no sign of concluding. Tomorrow you may wake to new discoveries, new insights, new evidence about what lies beneath. Or you may wake to the same mysteries, still unanswered, still inviting contemplation and wonder. Either way, the journey continues, and there is peace in being part of something so much larger and longer than any individual life, so much more mysterious than any complete explanation could capture. Sleep now, rest now, let go now. The deep earth keeps its watch in patient darkness, and you can trust in that immense stability, that ancient presence beneath all surface changes. Everything you need to know for this moment is that you are here, breathing, resting, part of the living earth, connected through unbroken lineages to the first life that emerged in some warm pool or deep sea vent billions of years ago. That is enough. That is more than enough. That is everything.